What will you do if your computer hates you? Okay, so this is the 6.5 E4 B.99 problem we're taking a look at with centripetal force. And if you recall, in a prior problem we did, problem 9.11, we were going around a turn, and the cops pulled us over. They said we were going too fast. They said we were going 45 miles per hour. We said we were going 35 miles per hour. We took it to court, and we proved to the judge that, based on the friction that we had on the ground, the max speed that we could go is 35 miles per hour. If we went any faster, we would not have enough friction to hold us in the loop, and we'd crash into a tree. Well, the officers have a rebuttal for us. They sent their best two detectives, Hitchcock and Scully, to prove that we were indeed speeding at 45 miles per hour around the bend. Okay? So they claim that the friction in the tires, between the tires and the road, didn't actually exist on the curve. They claimed it's a icy winter day outside. There's no friction on this turn. So our entire argument saying that there was friction is now thrown out. And what they're then saying is that the only reason you were able to go through the curve is because it was banked. So you were able to move through it at high speed of the 45 miles per hour or the 20.12 meters per second. What we are going to set out and prove is that these officers are indeed wrong because the angle of the curve that this thing would have to be built at would be ridiculous for an actual roadway. And we're going to prove that their idea is not correct. So let's take a look at this. We've got a few things here in this problem. We know the actual radius of the curve is 32 meters. So that's our radius of the curve there, 32 meters. We know that the officers think that we're moving at 45 miles per hour or 20.12 meters per second. So that is our linear velocity. And we know that there is no friction on the road here. But other than that, we are kind of in the dark. So let's try to figure out what is going to happen in this problem. So we know if we draw our banked turn, so here's the incline that exists, and then we kind of bank the turn away. We know this is set up at some angle theta, and if we draw in our car, we know that there's a weight acting on it, acting down, and we know that weight equals mg. We don't know the mass in this case, which is kind of weird, but we'll see that it might not actually matter. And we know there is a normal force perpendicular to the road here. Now, don't make the mistake that I've made in the past and that others make, where all of a sudden we're saying, hey, this normal force equals mg cosine of theta. This is the wrong problem for that. You only use that whenever we're looking to go up and down the plane. So if we're moving like this, our car is actually going around the turn. So don't make that mistake. Get rid of the mg cosine theta idea. We are going to use some SOHCAHTOA, but not in that way. What we have to recognize is that there is a normal force component, ny, acting up, and that a component of that normal force is acting to the left. We'll call that nx. And this is important because we need some inward acting force, nx, to bring us around the circle. That's our centripetal force there. So if we actually work this out, we see that ny is going to be equal to the weight of the object, our car, because if the weight is larger than the vertical component of the normal force, we'll sink into the road, and if it's the normal force is larger in that vertical component, then we're going to fly off the road. So they have to be equal. And we know that if we draw a little triangle here, this angle on the inside in green is the same angle that our road is tipped at. So we can quickly say that this is the opposite side, our adjacent side, and the hypotenuse, which gives us that ny is equal to mg, which is equal to n multiplied by the cosine of theta. And if you haven't watched our video where we derive this equation and kind of the setup here, make sure you go back and watch that. What this allows us to do, though, is it allows us to solve for the normal force. Our normal force equals mg, and then we divide each side by cosine. So we have mg over cosine of theta. If we do this in the x direction as well, we'll do it down here. The normal force in the x direction, that is going to equal the normal force, n, multiplied by the sine of theta, because that's our opposite side here. And knowing what n equals mg over cosine, we can substitute it in so that we're going to get mg multiplied by the sine of theta over cosine theta. What we saw in our derivation to this is that sine over cosine is actually equal to tangent. So we can write this as mg multiplied by the tangent of theta. And what's great about this equation right here is because that this nx, this x component of the normal force, is the force that is acting inwards towards the center of our circle, this is actually our centripetal force here. And if that's equal to the centripetal force, we know that it has to be equal to mv squared over r, because this Fc, our centripetal force, equals ma, where that's a centripetal acceleration. So at this point, we can start solving this. Let's go through and just rewrite it real quick. So we've got mg tangent of theta equals mv squared over r. And one of the things we might notice immediately is that the mass actually doesn't matter. The mass divides out on both sides, so it's gone. So it doesn't matter if we have a small little Volkswagen Beetle or a much larger truck. The mass has gone away here, which is awesome. That's why it wasn't given to us in the problem. And since we want to solve for this theta right here, that's what we're looking for, let's try to get tangent of theta by itself. We'll divide each side by gravity. So now that we have tangent of theta equals v squared over g times r, how could we get tangent of theta by itself? Well, what we can do here is, since tangent is a function, we need to use an inverse function to get it to go away. So on each side here, we'll take the quantity, so tangent of theta, and then on the right, v squared over gr, and we'll put that quantity into the inverse function. When we take the inverse function of each side, or the inverse tangent in this case of each side, the function and inverse function wipe each other out, leaving us with just theta. And on the right side, we just have the inverse tangent of v squared over gr, which, given the numbers we have in this problem, we can just solve this out. We can say that theta equals the inverse tangent of the velocity that they're saying that we're going at is 20.12 meters per second squared. If we divide that by g, that's 9.8. And don't forget to also divide that by the radius of the curve, which was 32 meters. This is a lot to enter into the calculator at once, so I'm actually just going to enter into my calculator the inside piece right here, the 20.12 squared divided by 9.8 divided by 32. That'll give us a little easier time to play with things. So 20.12 squared, I got 404.8. Then divide by 9.8, I got 41.3. And then we need to divide by 32 as well. And I get 1.29 on the inside there. Note that this term that goes into the inverse tangent function, this is unitless. There are no units on it, and that's how we know that we did it correctly. If we take a look at our units up here, they were like meters squared per second squared over meters per second squared times meters. So the second squared and second squareds go away, and a meter, 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 meter go away. It's all gone. Look at that. So that worked out very nice for us. And now we can just actually take the inverse tangent here. So let's take the inverse tangent of 1.29, and we get an angle theta of 52.2 degrees. That would be the angle the road would have to be at in order for us to stay on that bend going 45 miles per hour and not slide up or down the hill. To give you an idea of just how crazy steep that is, the roads or the track of the Daytona 500 is only pitched at 31 degrees. And those cars are like going around like this, right? They're like going through huge like bends there. Those are only pitched 31 degrees. We would need to be pitched like way up like this. And if you ever go around a bend like that, let me know. That's kind of wild and crazy. We want to see that road. So this is how we can approach one of these problems and kind of work our way through it. it's not too crazy in terms of setting things up. We just need to be a little bit careful in our SOHCAHTOAing and figuring out our equations to use for centripetal force. But once we do that, we see that the math is something that we've done many times before, and we can indeed work through it. Now, while we might not do something like this on a real road with a car, that's just a huge pitch of an angle, we do see angles very pitched like this in some certain situations, such as luges or bobsled races, like skeleton races in the Olympics for Winter Olympics. Those curves have huge angles that you pitch up on at the side because those lugers, those racers, are moving very fast. And if you live around my region, and if you've ever been to Seven Springs, in the summertime, they actually have something known as the Alpine Slide. And these are at other locations in the world too. But it's a large fiberglass slide that runs down the mountain like a luge track. And you just sit on a little plastic cart with wheels on the bottom and rocket your way down. These have bank turns as well that you'll slide up on them. And you need to be careful whenever you're traveling on them, because if you are traveling too fast, then your velocity will be greater, such that the angle of that bank turn will be too shallow for you, and you'll actually fly off the track. This happened to me when I was about 8 years old, and I slid 30 feet on my face, and that's why we're looking at this right now. So just be careful of that if you're ever doing something like this. But this kind of physics ideas do play into real life. The one thing we haven't talked about right here in terms of this physics in the real life is what happens with friction. We haven't talked about friction in this problem. Friction makes this a little bit more complicated because the friction is either acting down the plane or up the plane, which means that we need to break that friction into components as well. We'll be taking a look at that in a future video. We won't need it for this class, but if you want to dive into it, check it out. It's a pretty cool topic there. But just for the general idea of a banked turn, we are finished. Adios, and take it easy.